Hey everybody, Dr. G here. Today I'm doing a video on doing the NAMD tutorial. So NAMD is a molecular dynamics software package, and the folks who created NAMD made a really great tutorial for learning how to use NAMD. But you know, if you haven't done this sort of work before, some of it can seem a little daunting in the beginning. So I thought it would be good to do a video of basically just me going through the tutorial myself and telling you each step of the way what I'm doing and why I'm doing it. And basically I'll be sort of just thinking out loud as I do everything so that you can actually see someone working through the beginning of the tutorial. And I think just doing the very beginning, basically we're going to set up a simulation of a single protein in a ball of water, and then I'm gonna run that simulation on a remote cluster. Because I think it'll also be good to see how to run these things on a remote machine instead of just your local machine, because that's another thing that is a little daunting until you get used to doing it. So I'm also going to do that. So all right, I hope it's helpful. Alrighty, so as I said, we're going to learn about NAMD today. So here's the home page for NAMD. And of course, I'll include links to these different websites in the description. So here's NAMD, and here's the page where you can download VMD. So VMD is for visualizing molecular dynamics simulation data. And basically, NAMD and VMD, they're created by the same people, and they work together really well. So they're great to use together. So we're going to be doing a little bit with both of them. So I just wanted to show the download pages. Here is where you download the code for NAMD, and this is free software. It's really really great. So this is free software. You just have to you sign up with your email address just so that they can keep track of how many people are using it. But this is from University of Illinois Urbana-Champaign. So you don't have to worry about anything shady going on. It's all up on the up. This is good free software. It's really cool that this is available to everyone. Okay, so now let's get into the tutorial. Here's where you download the stuff for the tutorial. So this particular page here, you'll note that there's both the PDF for how to do this stuff, and then there are also the required tutorial files right here. So we're going to want those as well. So you need both the PDF that tells you what to do, and then you also need the files, because there's all sorts of, well, you'll see. We're going to use these different files to run simulations. So you have to download both. So that is that. Okay, so I have the tutorial open here just in a browser. So I'll use this. Now let's see. Oh, and here's the files. So I downloaded the files, and if you unzip it, you'll see that we have these different things in here. And basically 1.1, where we do the build. So basically you have to put together these systems before you use them. So we're going to do the 1.1 build, and then we're also going to do the 1.2 sphere. So basically we take the protein of interest and we put it inside a sphere of water, because if we're interested in studying biomolecules, if they're not in water, it's kind of not all that interesting to us, right? Because we're interested in what's going on in a biological environment. So if we ignore water, that's not too informative, right? So we have to put these things in a solvent. They have to be solvated in water. So that's what we're going to do there. And then finally, I'll take the files that we create in these first two steps, and I'll move them to a remote server where we're going to do some calculations. Basically, we'll run the simulation there. Okay, so let's get started. So one thing I should mention is that unfortunately Apple has changed their operating system to the point where software that was relying on basically VMD used to run beautifully on Mac's operating system, and it doesn't right now. Let's see, I'm running what am I running? I am running Catalina. So I'm running Catalina. So basically the solution I came up with is I'm going to run something called VirtualBox. And on VirtualBox, I've installed a Linux distribution called Ubuntu. So this is kind of the most common way of running a Linux operating system. So basically I have this thing right here. This is VirtualBox. This is made by Oracle. So again, this is trustworthy stuff. So I'm actually just going to do the entire thing in VirtualBox. So it's going to be as if I was on a Linux machine running Ubuntu. Okay, so VirtualBox, start that up. So here's the VirtualBox. As you can see, here is the environment that I've created. So it's like a computer within your computer. So this computer, although it's a MacBook that runs Mac's operating system, this is like a computer inside of my computer that does not run Mac's operating system. It runs Ubuntu. And so in that environment, VMD is going to run just fine. So I start the VirtualBox up. That little window now, that's the virtual machine that we'll be working on. Don't need to do anything with that. Okay, so Ubuntu's starting up. Okay, so you'll see now I'm on this is the desktop of my virtual machine now running Ubuntu. And I've already downloaded the tutorial files here. So what I'm going to do with that is, let's see if I double click this. I'm going to say that I want to extract it. And then extract, close. And now you see that this is called a tar file. So this is if you've heard of zip files, compressed files, where you put a bunch of files together and make them smaller. That's what that is. This is a tar file, and so now we have this folder full of files is what was in there. So now I can open that up, and you see that we have these same directories as before, right? We've got 1.1 build, 1.2 sphere. This is the same as before. So we're going to be using stuff from the 1.1 build, the 1.2 sphere, and then also this thing called common. That has some files that we're going to need as well. Okay, so let me get the tutorial open here. Okay, so here's our tutorial. So the tutorial is actually running in the Mac's native environment, and then we have the VirtualBox here. Okay. But you could absolutely have them both running in the VirtualBox, or if VMD runs fine on your machine, then you don't need to do this part. But this is something I'm doing at the moment. Okay, so here we have our tutorial of how to run NAMD simulations. So let's go down to, okay, you should read all of this stuff, right? I'm skipping over it now because I want to get to the stuff, you don't want to see a video of me reading to you. But this is all good stuff you're going to want to read. Okay, so if I go down to, here we are. First thing we're going to want to do is we're going to need to build the files that we need to run the simulation, right? So we're going to need to generate protein structure files. That's a PSF, protein structure file. And the way we're going to do that, here we go, now we're getting into it. All right, so the way we're going to do this, let's see. Alrighty. Yes. So the way we're going to want to do this is we're going to want to go into the 1.1 build directory with a terminal. Okay, so what's a terminal? Well, it's actually kind of good that I'm working in Ubuntu here because the terminal is that's a Linux thing, right? But you can do terminals on Windows machines and also Macs. So you'll just have to learn it for your particular platform. So if we fire up the terminal here, I have a little link here. There we go. Now I'm in it. Now this terminal can move around on the machine that I'm working on, right? So if I do pwd, present working directory, enter, it tells me I'm in my home directory. If I say ls, that lists everything. So ls is for listing things. So this is moving around using the terminal. This is a really important skill. If you're going to be running molecular dynamics simulations, doing that type of work, you need to be able to work with a terminal. Right? The point and click stuff, that's kind of for mainstream things like, I don't know, writing in Microsoft Word or something, right? But for doing simulations, things like that, you absolutely need to learn to use the terminal. Okay, so for example, if right now on the desktop, let's say I go CD. CD means change directory. So change directory, and then if I type DE, and then if I hit the tab key, there's only one thing DE could be. It has to be desktop based on where I am, right? When I listed everything, that was the only thing this could possibly be. So I hit DE tab and it completed it for me with the desktop. So if you hit the tab key, that's autocomplete. This will save you tons and tons of typing. And you know, again, if you're going to be doing this type of work, you really want to save your hands for typing as much as you can because you know, repetitive motion injuries are serious business. Okay, so CD desktop, and then I list, and look, these are the same files, right? There's MD stuff, this NAMD tutorial files tar file, and then there's the folder itself, right? We're seeing the same things that are on the desktop. So the desktop is just a way of visualizing what we can see with the terminal here. Another nice thing, like I said, I'm just going to tell you what I'm thinking as I do it, is if you want to make this thing bigger, if you hit Control-Shift+, see how that makes it bigger? That's another thing that'll really save on your eyes and neck if you're, you know, to make things easier to see. And that's also good for the purpose of this video. Let me make my VirtualBox a little bit bigger too. Drag that a bit. There we go. So now hopefully everyone can see this pretty well. So I'm going to try and make sure that everything stays large like this so this is easy to follow. Okay, so I'm still on the desktop. So now if I change directory into the NAMD tutorial files, so this is now I'm in the NAMD tutorial files directory, right? Present working directory, PWD, there it is. And you can also see it, you know, right here, right? It's to the left of the $sign here as well. It kind of tells me where I am. If I type ls to list everything, we see we've got these familiar files again. 1.1 build, 1.2 sphere, common, right? These are the things, these are these directories we're going to need. So the tutorial tells us, what does the tutorial say? Go to the 1.1 build directory, okay? So cd, change directory, 1.1, and then I hit the tab key, it finishes it for me. And now I'm in the build directory, right? I'll make this a little wider, maybe I'll make this a little smaller too. So on my machine, I think it's Control-Shift-. Oh no, maybe it's just Control-. There it is, Control-. So it's really just Control- and Control+, but I have to hit Shift to get the plus, right? Because that's if I don't hit Shift, then it gives me an equal sign. Okay, so this is maybe a little easier to see. All right, so we are in the directory that they told us to go to. All right, now what do we do? So they said to get into that directory. Then once we're in there, we're going to type VMD. Okay, so I have already installed VMD on this machine, therefore on the virtual machine, right? So I actually have 2 copies of VMD installed. I have one installed on my regular Mac environment, and then you know, it works better on the VirtualBox. I'll just say that it runs better in Ubuntu. So I had to separate it. I had to install the Ubuntu version in the Ubuntu VirtualBox as well. You have to do both, right? Because these machines don't know about each other. So if I go VMD, hey, check it out. So this is the VMD software here. So this is for visualizing things. So this is the window where we're going to see, you know, our molecules and stuff show up. And let's see, let's go back to the tutorial. All right, I've opened up VMD. Now what do they want me to do? Let's see, we want to load the 1ubq.pdb. Okay, if we want to load this, I use the main menu here. I go File, New Molecule, Browse. Okay, let's see, where am I? So this like / here, this means go up a level in your file system. And this is the same in the terminal. It's the same keyboard command. So if I click that, I went up a level. See, here's those files again, 1.1 build, etc. If I go up one more, now I am on the desktop, right? These are the files that we saw on the desktop. Oh, and down here it shows where we are too, right? So it says where we are. And it told us to, what did it tell us to bring up again? It said 1ubq.pdb. They want us to load that. So I'm going to load that. 1qb2. Okay, so I go back to tutorial files, 1.1 build. There it is, 1ubq.pdb. Double click that. Okay, and now you hit this load button, and let's see what happens. Oh, cool. All right, so there's a molecule. So this is ubiquitin. This is a protein. So this is just the the raw structure. We're going to have to do some stuff to this, but now we've loaded the raw structure. Let's see here. What do they tell us to do next? Oh, by the way, let me just tell you a couple little VMD tricks. So when you're spinning this around, so if you just left click and drag, it'll rotate it. But there's actually different modes here. So if I hit R, it's going to rotate, right? That's the default mode. So when you open up VMD, it's already in rotate mode. So rotate is R. And then if I hit T, so I just type T, now it's in translate mode. So I can pick this thing up and drag it around, right? I'm translating it across the screen. Right? That's a mathematical operation. So rotate, translate, and what is the other one? Oh, S. S is for scale. I can either scale this thing up or down. So basically make it bigger or smaller. It's, it gives you the idea of like kind of zooming in. So toggling between these different things, you can really get to exactly the part of the molecule you're trying to see better, right? So scale, zooming in, rotate it, spin it around a little bit, and then T, I can move it around, right? It's a little close. I'm gonna hit S again for scale, zoom out a little bit, T, I centered it. Okay, so those are the different modes that you can use here, right? And then of course back to R, because rotate's kind of the one that you use the most. All right, so that's loaded. Now what do I want to do? Okay, it's in there. What's next? Okay, so now they want us to use something called the TK console. So the TK console looks a lot like your terminal, but it's specific to VMD. So it's like a dedicated terminal that you're just going to be using in VMD for our purposes here. So, and it tells us to type these commands. Well, all right, let's first open up the TK console. So the way we do that, go back to our main menu here. We go to Extensions, TK console, click that. Okay, this is my TK console. So remember I said it's similar to a terminal, right? And some of the same commands work. If I go present working directory, pwd, enter, it tells me where I am. ls, it lists what's in here. Cool, so a lot of these same commands work. But there's also some commands that'll work that are specific to VMD that your regular terminal won't know what you want it to do. So let's see here. What does it say? Set UBQ. I'm going to put this over here so we can see both. Slide my VirtualBox over. There we go. So it's telling us that we want to go set UBQ, and then in brackets we put atom select top protein, and then a close bracket. Okay, so basically what we're doing here is we're setting a variable that we're going to call UBQ, and we're using an atom selection process that we're attributing to UBQ, right? So we're taking all the atoms that are part of the protein, and we're assigning them to UBQ, so that if I want to, so we're giving it a name basically. We hit enter, atom select 0, so I just did an atom select command. So basically now if I want to access the atoms in the protein, I can do that by calling it UBQ. And then that's what we do in the next line. So I access that variable with a $sign. And this is something you'll see in a regular terminal as well. So I hit $UBQ. So then what this means is, in fact, if I hit $UB and I hit tab, see it filled in the Q for me, right? Because the system knows what UBQ is because I just named it. So by using the $sign, I'm referencing what it's storing. I'm saying, all right, whatever UBQ is storing, I want you to do stuff with that. So we have $UBQ, and now I type write pdb ubqp.pdb. So what I'm doing now is I'm writing a new PDB. So there's one that we got, and it's the one that we see open here. And then if I do this, I hit enter. Okay, so what I did now is I created a new PDB file. So before we had only the one called ubq.pdb, right? But now if I go back here, let's see, I'm in the 1.1 build. See, there's the new one, ubq.pdb. So before I only had one ubq, right? That's what I started with. I just created this using the TK console. So we just made this. All right, great. So that worked. Now let's go back. What else? Let's see. Okay, this is the terminal window that's currently running VMD. So that you will see stuff in the background of what it's doing, but you can't close this. If you close this, you kill your VMD, right? So this terminal is what VMD is running in. So don't close that. Okay. What is next? Let's see. Okay. So we created that. Okay, so now it says that basically for this part of the tutorial, we've done the thing we wanted to do. So we're going to quit VMD by choosing File Quit. Okay, that's pretty straightforward. Let's go back to our VirtualBox. This is our TK console. We don't need that anymore. We can X that out. All right, this is the main menu. This is how we quit. So if we say, you can actually just hit the X here. If you hit the X, really quit, yes, I'm serious. There it goes. Okay, so now this terminal that was running VMD, it's still open, right? But now I can just do whatever I want here, right? I can say present working directory, it'll tell me where I am. I can ls to list things, it'll tell me what's in there, right? Oh, here's another trick that's very good to know. I use this all the time. If you type ls space dash, dash TRL, there used to be a TV show when I was a kid called Total Request Live. TRL, that's what everyone called it. That's how I remember it. So list TRL, enter. So what this does, this is the list command, but it gives you more information. The most useful thing that I really like about it is that it puts these things in order. So we look at the files. Look, this one goes all the way back to 2004, right? So this file is probably older than some of the folks watching this video. That's pretty wild. But anyway, so it puts these things in order of time, right? So we see 1939, so that's 7:39 p.m. So this is today. This is the thing that we just made, right? We just made this using the TK console. Okay, great. And so this is like a nice thing to do if you're working in the terminal or and you think you just created a file and you're not sure, do ls space dash TRL. It'll list everything in order, and if there's a new file, that's going to be at the very bottom. It'll be real easy to see if you have something new. So just a handy trick. So like I said, I'm just telling you things as I do them, as I think about them, so you can kind of see how to think about doing this type of work. Okay, next step, after we quit, right? So we were here, we quit VMD like they told us. Now they say, you will create the PSF file of Ubiquitin. Okay, make that a little bigger. Okay, now you will create the PSF file of Ubiquitin. Okay, so this is a protein structure file. The PDB files, that's the protein data bank files. And what that is, that's just people store, not just, but people store structures there. So sometimes if you say you've an experimentalist who does X-ray crystallography found a new structure. Well, X-rays, because of the size of their wavelength, relative to the size of a hydrogen atom, they can't really see hydrogens. So that's one thing that these PDBs that are in those that are in the protein data bank, they often don't have hydrogens on them. There can be other issues with them. Not all the information's there. Another key thing is that it just has positions. It doesn't say what atoms are bound to what other atoms. It turns out that VMD is very good at guessing where the bonds are based on where they are spatially. But if you want to do a molecular dynamics simulation, you don't want any guessing going on there, and that information does have to be given to the simulation software. Nothing is assumed, right? You have to tell the simulation software every pair of atoms that share a bond. And by the way, do they share a double bond or a single bond, etc. So there's a lot of information in a protein structure file that needs to be created. So there's a PSF. so that you can't just use a PDB for doing simulations. PDB is where we start. They're incredibly useful to us, but we can't, that's not enough. We also need to create a PSF. So, all right, so we're going to create a PSF file for Ubiquitin. Let's see, and the way we do this, VMD offers an automatic one. Okay, the way we're going to do it though, we're going to use this PSF gen package of VMD. So basically there's you know, protein structure file generator, right? PSF gen. So this is a bit of software that exists inside of the VMD software package, and we're going to write a script for it. So this is a little bit like writing code, but it's a little more higher level, right? So we're giving it a script to follow. We're basically saying, okay, somebody made this software, this PSF gen, and we want to tell the software what to do step by step. And these are the steps right here. And I do want everyone to, you know, take your time and read through what each line is doing, because, you know, if you're just going to go through and you know, just copy things and not really think about what they're doing and get it to run, then you haven't really learned all that much. But just for the purpose of keeping this tutorial to a reasonable amount of time, I'm going to be copying some things, but I want you to spend the time, you know, really figuring out what everything is. Make sure you understand what the script is telling the software to do. Okay, so what we're going to do is in this same directory here, we're going to create a file, and ultimately we're going to call this file, what are we going to call it? We're going to call it ubq.pgn. That's what the directions tell us to do. So the way we're going to do this, the tutorial suggests that you use, not gedit, what did they use? OpenNedit. All right, so there's, or NEdit, I don't know how you say it. But in fact, I call the other one gedit, but I think it might actually be gedit, I don't know. But basically, this is a text editing software. And already installed in Ubuntu is something called Gedit, and it does basically the same thing. I'm sure there are differences. Somebody could tell you. I'm not one of these people. All right, so let me make sure that my terminal is in the 11 build directory, and it is, present working directory, 11 build. And if I type, let's see here, if I type gedit, see how it opened this up? So it created this document here, and then they tell us to type these things into the document. So let's see here, what all do we have to say? Okay, so what they want us to do is basically just looking off of this, type exactly that into here, right? Okay, and then basically, and then you hit save. So for now, I'm just gonna write ASDF, and then if I save it, it's gonna ask for a name. I'll call this ASDF for now. Okay, and then I close it. And now if I list everything, you see now I have ASDF. So there's that file that I just created. So I did want to go through just the process of showing you how to save a file like this, but we are not actually going to type all that out, because if we look around, this file actually already exists in the tutorial. So, and by the way, if I wanted to open that up again, I can go gedit, ASDF, return, and then there it is. See, the file says ASDF, just as I left it. All right, I'm gonna close it again. Okay, so as I mentioned, this thing is already in here somewhere. In fact, let me remove this ASDF file now. So here's another terminal command we're gonna learn. Be very careful with this command, by the way. RM means remove, and there's no going back. It's not like on Windows or a Mac when you put something in the garbage can and you realize you didn't want to delete it, and oh, let me just get it out of the garbage. No, if you use RM, it is gone forever. There's no getting that back. It is gone. So be very careful what you use RM for. So if I go RM ASDF, and now I list it, now we see that that file is no longer there, right? That was a junk file. Just wanted to show you how to use gedit. Okay, and as I mentioned, let's see, what is in here? So this file is already created for us. If I go to cd change directory into example output, and then ls to list that. Now we see that one of the files here is this ubq.pgn. So if I say ubq.pgn, is that the one they wanted us to make? There it is, ubq.pgn. And as I said, I'm doing this to save time, but you really should make sure that you read what each step of the script is doing. And let's take a quick look at it. So if I go gedit or gedit, whatever it is, gedit ubq.pgn. If I open that up, what does it say? We have, let's compare it with this one. Package require, hey, it looks like it matches, right? So this is all the stuff that they told us to type. So we didn't have to type it because it was in there, but nonetheless, make sure you understand this stuff. But this is still a different teachable moment because what I could do now, so ubq.pgn, what I could do with that is I can copy that. So let's see here. So if I go cp, that means copy. And then I put the name of the file I want, ubq.pgn. So copy ubq.pgn, and then basically you have to say where you want it to be. Well, I want it to be up a level in 1.1 build, right? Because right now I'm in example output, but I want it to be in 1.1 build. So then to go up a level, I go period slash, and that should do it. And then I hit enter. Now if I go up a level, cd dot enter, and now I list ls, list everything. In fact, let's go list trl. Hey, check it out, ubq.pgn. That's the file they wanted us to make, right? There it is. So be sure that you are in the 1.1 build directory and enter the file name as ubq.pgn. Okay, so we did it a little differently, but we got the same result. We have a file called ubq.pgn, and it lives in the 1.1 build directory. Cool. Okay, what's next? Now they want us to, we're going to use VMD to run PSFgen. Okay. Oh no, sorry. This is the summary of what this ubq.pgn is doing, right? And I want everyone to read this carefully so that you know what the ubq.pgn script was telling VMD to do, right? So basically, we're going to tell you VMD to do all this stuff. We're going to do it in one step because we're just going to be like, hey, read the script, do all these things. But these are the things. This is line 1 through 9. Okay, what's next? Okay, the next thing we're going to do. All right, now we're going to use VMD in a different way. So in this one, now we're going to use VMD in text mode. So you see how the word text is here. So earlier we used the regular VMD mode where we, remember we were able to visualize the protein and we could spin it around and move it and stuff. But sometimes you want to do stuff in VMD that only requires text. And the reason why sometimes you want to limit yourself to that is because if you're working on a remote server where the only way you can interact with the server is through one of these things, through a terminal, then you may not be able to do visual things, right? Because these servers, if they let everyone run all kinds of visualization stuff, it could really bog down their servers. It could waste a bunch of computing power that could be used for calculations. So basically, you want to be able to run things in text mode as well if it's going to run on a server, and VMD is certainly something that needs to be able to run on a server. Okay, so let me get a little closer. Okay, so the command is VMD. Oops, let me move this down a little bit so we can see both. I'll move that up. So this is the command we want to run, vmd-dispdev. Okay, let's just do it. So if I go vmd-dispdev, the word text to tell it we're running in text mode, e ubq.pgn. All right, enter. Cool, it did some stuff, right? Let's see if I did the right stuff. Well, let's see what they say. Having run PSFgen, 2 new files will now appear. Okay, well this terminal is still running This terminal is still running VMD right now. So this terminal is busy. I could open up a new terminal and look, but there's other stuff that it says it does. Let me see. Okay, we're going to see some warnings. They're related to the ends of the molecule. They said this is cool. Don't worry about it. Don't worry, don't just make a habit of ignoring warnings all the time, because sometimes this can be a very bad thing. But in this case, it's okay. Okay, but it says our system should have 1,231 atoms. Let's look for that at least. Yeah, 1,231 atoms. Cool. So it looks like it did the right thing. So we ran this thing, and let's see. I think we could probably exit out of VMD now. Yeah, it says we can do this. Right. Yes, yeah, let's get out of here. Okay, so we ran VMD here. So if I just type exit, enter, now this terminal stopped running VMD. Now it's just back to being a regular terminal. So now let's go list ls-trl, see what we have. Let's see here, 7:54. Yeah, right now it's 7:55. This was made at 7:54 p.m. So yeah, we just made this PSF file. Okay, cool. So things seem to be working. This is wonderful. All right, what's next? All right, now we need to solvate the protein. So as I said, the goal of this exercise is ultimately we want to run a simulation on a compute cluster, right? This could be a local computing cluster at a university, or it could be a giant supercomputing center, right? You interact with them in basically the same sorts of ways. So let's see here. Okay, so solvating the protein, we need to put it in water. So how are we going to do that? Well, there's different ways to do it. For the purpose of today's exercise, we're only going to do the water sphere example. The water box is actually kind of the more common one that you're going to do more. But I just kind of wanted to get everyone started, so I thought, let me just show you how to do it with the water sphere. Okay, so the way we do this, let's see. Okay, now we're going to use a script, wat underscore sphere.tcl. Okay, so this is a script that we are going to run using VMD. So there's another script we're going to give to VMD. Let's see. So it says it's in here. It's in the 1.1 build directory. All right, so let's take a look, see if we can see it. Okay, so now I can just see it just looking at this, but let me show you another trick for using the terminal while we're doing it. So let's say that I wasn't sure it was there, and I was pretty sure that it was the only file that had TCL as the file extension. If I go list, and then I hit the asterisk is like a wild card, and then I go, what was it, TCL, right? TCL, and I hit enter. It's only going to list things that end in TCL, right? I could have done that with PDB, right? Now list 3 things because I have more things like that. But so that's just another trick I wanted you to be aware of. Okay, so there's water sphere TCL. Let's see what it looks like. Let's just take a peek. Can it water sphere? Open that up. Hey, there it is. So this is what this script looks like. So this is a script that will take your molecule and put it into a sphere of water. That's pretty cool. All right. So this was written by the people who created the software and specifically who created this tutorial, right? So let's see what they want us to do with this script. Probably just run it. Yeah, there it is. So I'll put this up at the top so we can still read it. No, we can't quite read it. Fix that. There it is. All right, so we're going to want to follow this script, vmd dispdev. Right, we're running in text mode again. And this time we're going to do the water sphere. Okay, so they say, let's see here. Okay, we're in the right directory. vmd dispdev text. Water sphere, TCL, all right, and enter. Cool, it's doing all kinds of stuff. Great. All right, so this is all the output as it runs. And by the way, running molecular simulations, things spitting out a bunch of information, this is something we see all the time, right? If you've only previously used things like Microsoft Word and just kind of stuff for just general users, usually when things start spitting text at you, like you feel like you're in trouble, you've done something wrong, right? But it's totally normal with software that's written for scientists and just more technically savvy folks. Okay, so what did it tell us? So it gave us some information here, the center of mass of the sphere and the radius of the sphere. If I remember correctly, we need this information. So let's see here. This will do this. Okay, so put ubiquitin in the smallest possible water sphere that completely covers the protein. All right. Okay, the output will be the center and radius of the sphere. Record these numbers. Okay, they want us to record these numbers. Well, in that case, you know what? Why don't we just let's create a file with this so that in case we forget it, we have it, right? So if I hit this little plus sign here, this adds another tab to my my terminal here. So these are two separate terminals, right? I have this terminal, I have this terminal, and they're independent. They're doing different things. Oh, you know what? Let me make this one bigger. So this is Control Shift plus. There we go. And the shift is basically selects the plus instead of the equals sign. So I don't know if I should call that shift, but yeah, you do have to hit Control and Shift. Okay. So, oh my goodness, I cannot get this thing the right size. One more try. There it is. Okay, finally. All right. Present working directory. We're in 1.1 build, list, TRL. There's everything here. Okay, what do they want us to do? Oh, right. We were going to save this information. So they told us that we need this information. So I'm going to highlight it. Oops. Highlight. Copy. Go to my other terminal. And now I'm going to go get it. Gedit, whatever it is. I have a new document. Now I'm going to right click, paste. There we go. Now we have this information saved, or somewhere saved. So I hit save. Let's call it sphere data. Save that. And then we close it. And then list TRL. There it is at the bottom. There's sphere data. Let's see. And you know what? I'm going to change I'm going to put a file extension on sphere data because it looks weird to me. So this is another opportunity to teach you a Linux command, or a terminal command. So mv means move, but you can also move one file to a different name. Basically, like the move command can also be used to rename things, is what I'm trying to say. So if I say move, so all I have to type mv sph tab, and then it finishes it for me, and then sph tab again, and .txt for text. So this says move sphere data to sphere data.text. So I run that, and then if I list everything again, now we see that it has a new name, sphere data.text. So I've renamed it something a little bit better, which I probably should have named it that in the first place, but now I got to show you how to do that. So that's good too. All right, let me show you one more thing. So there's another thing called cat, which is short for concatenate. And basically that means take a file and just dump it out to the terminal. So if I say cat sphere data, enter, see how it dumped the contents of sphere data out to the terminal. So if I don't want to open the file to read it, I can just dump it to the terminal. And be careful with this. If it's a giant file and you dump it to the terminal, it's going to take it, it's going to dump everything out to the terminal. And if it's a really long file, that could take a while and it can be bad. So be careful doing this. But I knew it was in there. So, all right, now what do we do? So save those numbers. We need them. Great. Okay, we're done with VMD out. Okay, so it says now we can leave the text version of VMD. So here we are in our first terminal, right? I opened a second tab to do this stuff. in our original tab of our terminal. Here we are. I type exit, and we're out. Okay. Now what do they want us to do? Okay, now we are going to launch the graphical version of VMD. I bet they want us to take a peek at what this thing looks like. I'm kind of excited to see it. All right, so we're gonna have to load. All right, we'll follow the directions when we get to it. So for now, we just open the regular version of VMD. So just type VMD, enter. Now we're running the regular VMD. And now they say to first open ubqws.psf. So I think that's water sphere. UBQ water sphere is probably why they named it that. File, new molecule, browse. Okay, where are we right now? I'm gonna go up a level, 1.1 build. I know I want to be there. Okay, I guess we were in the right place. That's fine. ubqws.psf, right? Yes, ubqws.psf. That's the one. ubqws.psf. There it is. If I double click that, and then I say load, okay, it doesn't show us yet, right? Protein structure file is all sorts of very important data for the structure, but it does not have our X, Y, and Z coordinates, which VMD needs to show it to us. So what's next? Okay, we did that. Okay, now we're gonna load ubqws.pdb. So now we need that too. There it is. Load. Hey, check it out. This is pretty cool, I think. All right, so we have our ubiquitin molecule inside of a ball of water. So this is like a really, really tiny droplet of water. And again, it's in rotation mode. You hit R to get that. And you don't have to hold this down, by the way. You just press it once. If I hit translate, I can move it around that way. S for scale, or sorry, that was T. T for translate, S for scale. Zoom in, cool. In fact, while we're playing with how this thing looks, I'll show you one other thing you can do. I can go to display. No, not display. Graphics, representations. Let's see, yeah, there's only one in there, good. So basically representations, this allows us to kind of play with how we're seeing this. So for example, if I double click this, whole thing went away, right? I can also I can create a repetition of this. So if I create a new one, now there's two versions of this, right? So if I turn one of them off, you can still see the other one. I have to turn both of them off. Then we can't see anything, right? But turn them on, and now you see the selection here. So I'm just going to do, let's see, so for the first one, I'm going to turn this one off for now. And we're going to go to this one. So we're in this particular one. This one's not doing anything at the moment. So it's showing us this. And for selected atoms, I'm going to say, what if I say not water? Enter. Okay, see how the water went away. And there's all sorts of different selection commands you can do. You can and or not, all sorts of stuff. But not water was kind of the easiest thing to do here. So I said not water. And then how about for this one? Let me turn this one back on. And then let's say I make this one water. Cool. So now if I turn this one off, so we just have the water, and you can tell it's kind of hollowed out where the thing was, right? The protein, ubiquitin. I can turn it back on, I can show up again. One more little thing, let's change the drawing style of the ubiquitin here real quick. So drawing style, I like licorice, where is it? Licorice. See that? So now we have our, and let's hit the scale mode so I can zoom in a little. R to rotate again. So I can kind of look at this thing. Well, that's kind of peeking out a little bit there. Well, I guess they did say it was the tiniest water droplet you could get that totally covers it. So it barely covers this part that's extended, but I guess technically it does succeed. Cool. All right. So anyway, I just wanted to show a few quick VMD tricks for looking at stuff. So I encourage you to play with that because it's fun, and I don't know. It's also useful too because when it's time to share your information of what you learned from your simulation, oftentimes the pictures are the most important part. So pictures of the molecules, pictures of plots of the energy changing over time, or some distance that you care about changing over time, something like that. Anyway, where are we? Okay, so I think that means we can close this out. So let's just exit out really quick. Yes, really quick. Okay, so this UBQWS conf, so this CONF, I think configuration file is what it stands for, I believe. That is that's a script, right? So I showed you that we've worked with scripts, like with the TK console, right? You gave it a script. There's that step where we give it 9 things to do in one shot, right? Well, you do the same thing with NAMD. There's all sorts of different parameters you have to give NAMD. You have to tell it, what temperature is the system running at? How many time steps do you want to simulate? All sorts of things like that. But the intelligent thing to do is put all that into a script. So, okay, so go to your 1.2 sphere directory, and there you're going to find the configuration file for the minimization and equilibration of ubiquitin in a water sphere. Okay, so let's go there. So back to our terminal here. All right, we're in the 1.1 build, present working directory, 1.1 build. So not all shells. So another name for a terminal is a shell. Not all of them tell you where you are as you go. I'm sure there's a way to turn it off here. I haven't looked into it yet, but you can turn that on and off. So that's why this present working directory is a helpftle thing to have. And sometimes I'm working on shells that don't have it, so that's why I'm in the habit of doing that. Okay, so if I go up a level, cd .. I go up. Now I am at this level, and I know that I'm going to need, where was it? It was in 1.2 sphere. We need a configuration file for the minimization. There we go. This is the one we need. Open the configuration file. Okay, yeah. So we're going to do that. We're going to do this step right now. Open the configuration file, ubqwseq.conf. Okay, so that is in 1.2 sphere. So cd, change directory, 1.2 sphere. ls to list everything, and sure enough, there it is. It's at ubqwseq.conf. Okay, so if I say get it, ubq, there it is, enter, that's going to open this for me. Okay, wow, look at all this. So let's see, and I can scroll through here. So this is the script. This is the thing that's going to tell NAMD what to do. And in the tutorial, they explain what every line does, I believe. Yeah, they go through every line and explain it. So you need to read that. Make sure you understand what you're telling NAMD to do, right? But again, for the purpose of the video tutorial, the video is more just to sort of show you what things look like as I go and tell you, how I'm thinking about it. So I don't need to, read that to you for now. So just looking through here, couple things that I'll point out a couple important things, but won't look at every line. So here we have structure files. So protein structure file, PSF. It's important to be able to find that. Note that it says go up a level to the common folder, and then that's where you'll find it. And same thing for the coordinates. They say to get the coordinates from a PDB file. That's a super common way to get your coordinates. So go up a level, go down to the common file, and then within the common file, you'll see this PDB file. Okay. So this is relative to the directory where the simulation is running. So wherever I put this conf file, that's sort of its home base. So I have to make sure that I have this common directory, and then I at least have the files that it needs from the common directory, right? So we're going to have to make sure we bring those with us, the files in the common directory, at least these two. We have to make sure we bring those with us when we move over to the server, where we're going to run these simulations. Okay, so that's an important line to note. Again, here's the temperature. There's the output name. Basically, molecular dynamics simulations produce a bunch of files typically. Like, you run one simulation, and then after it finishes running, you'll see that there's like maybe 6 new files in the directory, something like that. and they all have the same sort of beginning of the file. So this one, we're going to give it this name, ubqwseq, and then there'll be different file extensions on that, maybe some extra stuff as well. That's why that's there. Setting the temperature, the size of the time step. They're doing 2 femtosecond time steps, which means that you need to keep some bonds rigid because that's kind of a larger time step. Yeah, I don't want to get into too much detail there. We're using Langevin dynamics to do both the dynamics, and there's also going to be some other things we're using this for to monitor the pressure and the temperature as well. Let's see. Okay, other things. The restart frequency. Basically, as these simulations run, in case they crash in the middle, you never know what will happen. You know, who knows? Maybe the server goes down in the middle of your simulation, and let's say your simulation was running for a week and had 2 hours left, and the server goes down. You don't want to lose everything, right? So what this does is it sort of it saves different stopping points where it produces a restart file. And then basically, if the simulation crashes after it created that restart file, you can always start from that point. And then, you know, it keeps making these things as it goes. And so basically, every 500 steps, it's going to make a new one of these things. So that's a good thing to do. Okay, DCD frequency. This is how often the positions of the atoms are going to be stored to the DCD file. The file that stores the trajectories of, you know, where all the atoms are at every point in time, that's called a DCD file. And for both of these, really, you don't want to output too frequently to these things because that takes time to do it, right? It takes the computer time to do that. So you know, if you don't save your restart files often enough, you run the risk of, you know, losing everything if your simulation goes down. But if you run it too frequently, you're going to slow down your simulation to the point that that's no good. DCD frequency, same thing. If you want to capture how detailed the motions are, you want a really high DCD frequency. But if you do it too high, it's going to spend all its time writing DCDs, and your simulation is going to take forever. And if you make that too infrequent, then it's going to be, you know, a choppy simulation. You're not really going to be able to see how things are moving in enough detail. Also, the energy is outputted every, in this case, 100 steps. So that's why we have 100 on this line, is every 100 steps output the energy. So there's going to be some file where all the energies are. And again, this costs computation power to calculate what the energy is. So you don't want to do this too frequently, but you want to do it enough that you get the information you need. Okay, what else do we have? Okay. All right, so we have the center of our sphere here, spherical BC center. I bet we're going to need to go in and change that number. Maybe. Because remember, they told us to save that number. Okay. Minimization steps. This is an important thing. Basically, if two atoms are like really close to each other, the repulsive forces between them can be really high. And sometimes, you know, the positions that some of these atoms start in are actually really high energy positions. And if you ran dynamics on that with, you know, these time steps that we're doing, your simulation would be numerically unstable. You'd have some crazy calculations going on that, you know, maybe infinity would be the answer, and then the computer doesn't know how to deal with that. It can't store those numbers. It's something called an overflow error, or if it's too small, it's an underflow error. Basically, the simulation can crash. So you always need to minimize these things first. So this line says to minimize 100 steps before doing the simulation. And finally, at the end here, it says to run the simulation for 2,500 steps. And then here they put a comment. By the way, this little, you put a pound sign first, and then that's a comment. So 5 picoseconds. Basically, what they're saying is that given our step size of 2 femtoseconds, then that means 2,500 2 femtosecond steps adds up to 5 picoseconds. So that's why that's there. Okay, great. So this is the conf file, the confirmation file. So let's close that. So basically, they've already written it for us. So this is the file we're going to run. Let me check and see if they tell us to change the center. Let's see here. They told us to save that information, so I think they want us to reuse it. Okay, here we go. So it says, let's see, we're on page 23 here. Spherical boundary conditions. Okay, we're going to leave it however they put it. I think they had turned it on. Spherical boundary conditions center. So they want X, Y, and Z of the center. And this is why you need to record the center of your water sphere after you solvate. Okay, so we better go in there and change that. So let's see. Let's open up both of these things here. Let me, oh, here's the center right here. Okay, so we have these 3 points here, right? So let's copy them. We saved them in the file, but right here I use the concatenate to dump it out to the screen. These are the X, Y, and Z. So if I highlight that, copy, and now let's open this up again, this conf file. Okay, spherical boundary center. Okay, let's go down here. Let's go that. Now if I paste that there, okay, now we have these numbers. So are they pretty close? Yeah, they're real close, but we might as well make them accurate, right? So what I can do is I can use a comment to turn off the one that they used. So now this is just a comment. This no longer gets read. And now I have to make this say spherical BC center. That's the command. So if I copy that, copy, paste. There we go. Spherical BC center. Now we're using these values. And they're separated by commas. So let me add commas so that it's like theirs. Oh, you know what? How many spaces did they use? It might not matter, but just in case it does. Let's see, R1, 2, 3. I don't think it matters, but 1, 2, 3. I might as well be consistent. There we go. Cool. Put a comma and another comma. Okay, and there's nothing at the end. All right, so now we have replaced their center values for ours. As you can see, they're very close. So if we ran it without changing this, it probably would have run fine. But it's better that we're working with the real numbers. Okay, great. So let's save this. Okay. X that out. Okay, now I'm going to copy this thing. So because as I mentioned, you run these simulations, you want all your files in the same directory typically. As we mentioned, we are going to access a couple files from the common directory, so we'll bring that one with us to the cluster, let's to the HPC. But for now, let's copy this. So CP for copy, UBQ. Let's go up a level and then down to 1.1 build. There we go. So now change directory CD dot and then 1.1 tab list -trl. There it is. There's our new thing there. So I think we're now ready to run on the cluster, but let's make sure we haven't missed anything. Yeah, we're ready to run. Okay, so this is the command to run. All right, so what we need to do now is we need to get on the server here. So we're going to use the server at San Jose. Let's see, let me make a new tab. Yeah, I'm going to leave this one where it is. Actually, this one, we won't need this one anymore. So let me change this one. Actually, no, I'll stay. No, let me go up a level. Kind of doesn't matter where I am. Okay, so now I'm going to go, let's see here, SSH. That's for a secure shell. Username. There we go. So I'm just logging into a, there we go. So now this particular terminal is now, this is not on my computer. This is on a server in San Jose State's campus. So if I type ls here, see, we didn't see this before. Perl 5, you don't remember seeing that on my computer, right? Present working directory, right? So I'm in a different place now. And let's see here. I'm going to make a new directory. So that's mkdir, make directory. So I'll make a new directory and let's call it, I don't know, let's go video files. Video file. Well, no, I don't want to call it that because I think there's videos in there. Let's see here. NAMD for video. By the way, note that when I name a directory, I don't use spaces. Never use spaces in the name of a directory because it won't work well with the terminal. I'll use underscores if you want to put a space. So mkdir, NAMD for video. And now if I list ls, I see that we have this new one, this NAMD for video. And I can type ls NAMD for video. And then we see that there's nothing in there, right? That's empty. When I hit list, nothing showed up. Okay. So now let's put something there. Well, let's see. What I need to do is I need to copy, let's see, I need the 1.1 build directory, and I also need, let's see, I also need the, let me think, common directory. All right, so let me go up a level. Let's see, now we're here. Okay, I'm going to make a new directory, mkdir, and let's call it stuff for HPC, high performance computing cluster, right? So I'm going to make that, and then I'm going to copy stuff into that. So let's copy. So I want to copy the directory and everything inside it. So the folder 1.1 build, I want to copy the folder and everything inside it. So I need cp-r for recursive. So that means copy the folder, then if there's anything in that, copy that too. If there's anything in that, copy that too, right? That's why it's recursive. Okay, anyway, so copy recursive 1.1 build and copy that into stuff for HPC. First I'll do that. Then I'll do the same thing, recursive for common, and I want to put that also into stuff for HPC. So if I do that, now let's list everything in stuff for HPC. ls stuff for HPC. We see there's two things in there. These are the things we need. Awesome. So how do I move this? Well, the way I can move this, right, because this particular terminal, this is local. This is on my computer, right? This terminal is not on my computer, right? This is on the cluster, right? They're actually quite far apart right now geographically. Yeah, this is pretty cool, right? So anyway, the way I do this is I'm going to make something called a tar file. So I'm going to use the command tar, T-A-R, -cvf. So create verbose, and to be honest, I just blanked out on what the F is. I've been doing this for so long, I just blanked out on what it is, but don't worry about it. tar-cvf, and then I have to give the file a name. Whoops. I'll call it stuff for HPC.tar. Make sure it's .tar. To give it a file extension, and then you give it the file that you want to make a tarball of. So this is sort of the way people say it. Oh, make a tarball. So I'm going to tar this up. Tar CVS or CVF stuff for HPC. So now I give the directory that I want to get tarred. So first it's the file name, then the directory I want to get tarred. Enter. And because I typed the V in there, that verbose, that's why it said all this stuff. This is the verbose way of telling me what's going on. So now let me list. Okay, cool. So now you see that we have this stuff for HPC that wasn't there before. So if I want to get that on the server, what I need to do is I need to use another command called scp. This is secure copy. So remember, copy was just cp. This is secure copy because I want to copy it from one place to another and do so securely. So let's see. So I need to go scp stuff for hpc.tar, username, and a colon at the very end. So username at spartan01.sjsu.edu and then colon, and enter. Now it asks me for a password. Enter, and right now it's transferring it, right? So it's at 36% transmitted. And now let me jump on the other side here. So now again, remember this terminal is on the server here, right? So if I hit list, let me hit CD, and then CD enter is change directory to your home directory. If you don't tell it where to go, it goes home. So CD enter, and then list -trl, and check it out, stuff for HPC. This is the thing I just sent using secure copy. And we see that that just finished sending. And okay, so now we are ready to run the simulation. All right. So now that we have the stuff that we need to do the simulation in this stuff for hpc.tar file right here, let's unpack this thing. So let's move it first. Let's move it mv to move stuff, and then we'll put that into the NAMD for video directory that we made. So move that there. All right, so now if I list everything again, we see it's no longer there, right? So I'll go CD into name, NAMD for video. Now that's there. Okay, now to open this up, I say tar-xvf stuff. There it is. Open that up. Now we list that stuff. Okay, so now let's go into stuff for change directory, CD stuff for HPC. Let's go there. Actually, no, let me go back. First thing I'm going to do is, so when you transfer files using tar files, if you don't delete these things, these are going to pile up, and we don't want to waste space on our accounts on the Spartan HPC. So a good habit is once you've transferred the file and you know everything got there okay. Here, let's just list everything. Yeah, there's stuff in there. So it's a good habit to just delete the tar files once you don't need them anymore. So rm for remove .tar. Now I listed it's gone. Okay, so this is good. All right, now let's go into stuff for HPC. Okay, and let's go into the 1.1 build, because this is where we put everything that we need to run. So you remember that we have this this conf file. This is how we're gonna. This is the script that we're gonna give our system to run. Now, because this is running on Spartan in a regular terminal, that I haven't enabled visual stuff, which you can do, but I don't think I've done it. Let me see if this will open with gedit. I don't think it will, but let's try it. Yeah, cannot open display. So there's another way to open files, and so the editor that I actually most commonly use is something called Vim, V-I-M, and that's the editor that I mostly use. I used that gedit or gedit, however you say that, just because it's kind of an easier thing to use, and I wanted to try and use tools that were easiest, since this is for students just getting started for this video. But one thing that always works if you're on a remote server like this is Vim, or the VI. So the original version was just called VI, and then a more modern one was called Vim. But you access it by just typing VI, and then the name of the file you want to open. So I'm going to show you this real quick, just as another option for editing files when you don't have display things working for you, right? So let's try this. So if I do that, see now here, the terminal has become the text file. And I can scroll through this thing. And sort of an interesting thing with VI is, and maybe I'll put a link in the description of, maybe I'll try and find a video on how to use the VI editor or Vim. But the down arrow is actually the letter J. If I hit the letter J, it scrolls down. If I hit the letter K, it scrolls up. So those two are right next to each other. And then if I want to go to the right, I hit L. If I want to go to the left, I hit H. So I'm moving around on the screen using these letter keys. And you'll note that you might say, like, well, what if I want to type the letter J and instead of moving down? Well, then there's different modes for the VI editor. So what I would do is if I hit the letter I, this puts me into insert mode. So you see how that word insert popped up at the bottom? So now if I go down here and I hit, say, J, right? Here's a bunch of J's. You know, it's not moving the cursor around, it's typing the letter J. So I'm going to go delete those with backspace. So when you're in this mode, you can kind of, you know, just type like fairly normally in the insert mode. So then to get out of insert mode, you hit escape. So now I'm back. Now J is down and K is up again. So that is sort of a basic thing with the VI editor. So then you might say, well, how do I get out of here? What if I want to just go back to what I had before? What if I want to go back to the terminal? I'm done looking at this file, right? Well, then what you do is you type the colon. So I type the colon, and then if I hit Q, exclamation point, that means quit and don't save any changes that were made. So this is a good thing to know, because if you open up a file in VI Editor and you're still getting used to using Vim, you'll probably accidentally screw up files. So if this happens to you, just hit escape to get out of edit mode, and then you hit the colon, and then Q exclamation point, enter, and then now I'm back to the terminal. And then this file was not changed, right? So any changes that I may have made right there were not saved. But now let's say, let me open this up again. Let's say I did want to save a change. So I'm just gonna go. Let me go to the end of this line right here. Ubiquitous in a water sphere. In a water sphere. Another nice trick is if I type let's say I type the number 33. I hit 3 twice there, and then I hit the L button for moving to the right. See, it moved over 33 times. So that's kind of a handy trick too. So if I want to go all the way to the bottom of the file, and you know, maybe I'll just hit 9 a bunch of times, right? So you know, maybe I hit 9 a bunch of times, it's like 9,999, whatever. And then I hit J to go down. It went down that many times. Now, granted, it hits the end of the file, so it can't keep doing it. But that's like kind of there's actually better ways to do this, but like, you know, there's a command that takes you to the bottom, there's a command that takes you to the very top. And sometimes I forget what they are, and you know, that's just kind of a way to do it if you blank out on it. It's only an extra couple of keystrokes. Okay, but let's say I want to make a change here that I want to keep. So I hit I to go insert mode. And now let's, this is just a comment. So I'll just say GG comment, right? So now I've done that. And now I hit escape to get out of insert mode. And now I hit the colon again. And now if I want to quit and save that, I hit WQ. So that's write, quit, like write, W-R-I-T-E. So write and quit, and then if I hit enter, so now I'm back to the terminal. Let's look at it and see if that's still there. If I look at it, there it is. GG comment is still there. So that did get added. I'm going to take it back out now. I'll go back into insert mode, go here, and I'll just use the backspace to delete that. There's actually keyboard ways of deleting stuff too, but that's kind of the most straightforward thing, is to just use the delete key. Okay, so then I hit colon, write, quit again, so that it writes the fact that I deleted that. Okay, now we're back to normal. Okay, so that was just, I wanted to show you a little bit of VI Editor. So, you know, when you're working on your local machine for editing files, using something like gedit probably makes more sense. But when you have something that's already on a server and you want to make some small change to it, like you ran the simulation and you realize the temperature was set the wrong number, right? You wanted to change 300 to 310 or something. Then that's a perfect time to use Vim to edit it, because you just have to make a small change, and it makes a lot more sense than like moving the file to your local machine, then moving it back just so you can use gedit. That doesn't make any sense. You know, just use VI to edit it. So it's definitely worth spending some time to learn at least some basics of using Vim, the VI editor. Okay, so now let's get back to running the simulation. So let's find where we were in the tutorial. Where is this thing? No. There it is. Okay. So where were we? Oh man, we lost our spot. And by the way, something I should have mentioned: if you're using functions like SCP to secure copy things to the server, or you're using SSH to access the servers remotely, you're going to need to use this thing right here, this Cisco AnyConnect. So what this is this is our VPN. So it routes our internet traffic through campus. So it's a very smart move. If you have a server like this set up, is that you set it up so that it only can be accessed through campus. But of course, we don't want to have to be on campus to work on a computer. That doesn't make much sense. So the way around that then, so basically it's for security. The internet, you have to be going through the San Jose State's internet, but you can do that from home. You just have to get routed through there using a VPN. So anyway, make sure you're signed into the VPN for doing that. So actually I had an issue with installing my VPN. I fixed it, but that's why I have to find where we were in the tutorial again. So I stepped away and then something happened with the VPN. Let's see. Okay, there it is. Okay, so this is the command. So in order to run the simulation using this, so NAMD2, UBQ, all this is the command we're going to use to run the simulation. But we're going to need to do some stuff first. So there's a few things we have to be concerned with here. One is that basically, when you're working on a server, right now where I'm signed in, this is the sign-in node, or the head node is what it's sometimes called for a server, a compute server. And what it is we call these things computing clusters because it's a whole bunch of computers stuck together, actually kind of like this picture right here, right? This is what a compute cluster looks like. There's a bunch of computers in racks, and they're all running fans. It's actually quite noisy. So there's all these computers running, and that's what I'm signed into here, right? Is using SSH to access it remotely. I am now in one of these computers here. But so you see that there's these racks of computers, and the way it works is that you dedicate just a couple of the computers that are hooked together as head nodes, NODES. And what that means is these are the computers that are part of the cluster that are just used for like signing in and stuff like that. So a really big faux pas in working with these things, a really big thing you do not want to do is to try and run a simulation on the head node. So if you just sign in and then just start running like computationally intensive things, everyone's going to be mad at you, and you'll probably get booted from the server, at least temporarily. I don't think they'll throw you off for making this mistake once, like permanently, but basically it's kind of one of the, what's the word? It's kind of an inconsiderate thing to do, right? Because people need this node to sign in on, and if you're bogging down that computer by running some calculation, then that's, you're misusing it. It's used for people to sign in, and then everyone else who's trying to use the server is going to have problems using it. They're going to get bogged down. They're not going to be able to do the things that they need to do. So basically, the way these compute nodes work, or the way these clusters work, is that you have this head node that's just for signing in, and then you have to request the resources that are used for computing, and they call these the compute nodes. These are the ones that do all the heavy lifting. And there's different ways to use them. One is that you can submit a job script. And what that does is it automatically puts your job in a line, and then it's all automatic. It kind of like waits its turn, and then when it's the turn for your job to come up, then it allocates some of the computing power to your job and runs it. But another way to do it is to run with an interactive setup, and basically that says like, hey, I want to use one of these nodes for a bit, and so this is something where maybe you want to test out something. Like you've been working on this code, and say you have this big simulation you want to run that's going to go for 500,000 time steps. And you want to make sure that it works right before you really set this thing up. So it's going to go for 500,000. So maybe you knock that down to 5,000 time steps temporarily. And then you request an interactive node and you run it on there. And then you see if this thing works for 5,000 time steps. And then if that works, then you set it to 500,000. The same script, you leave everything the same, and then just change that number to 500,000 time steps. And then you submit a job that waits in the queue. So that's kind of some of the strategy with this. So because this is a short simulation that we're just kind of trying to test things out and see if they work, I'm going to request an interactive node. So the way you do this is, here we go. So just looking around online, so there's the software that's used for managing the compute resources on here is called Slurm, S-L-U-R-M. So what Slurm does is, that's sort of this is the software that manages how the computing resources are being used, right? So if you submit a job and it's sitting in a queue waiting for your turn, then Slurm is the thing that's handling all of that. And so if I want to request an interactive node, I also use Slurm for that, right? Because this is sort of these are the keeper of the computing power. So this is actually exactly what I want to use right here. So I'm just going to copy this exactly. Oh wait, I'm gonna have to type it in because I can't cut and paste between my my virtual node and my virtual machine and right, because just to remind you, like, this box right here is running Linux. This I opened the browser in just my regular Mac, so I can't copy and paste that. So I'm just going to type it in. I don't think I can. Anyway, let me try it real quick. I don't think I can though. Let's see. Copy. Yeah, it didn't work. All right, so I'll just type it in. srun -- nodes equals 1. And I'll tell you what some of this stuff means as I do it. So this says that the number of compute nodes I'm requesting is just 1. The number of tasks that I'm going to run on per node, I'm only going to run 1 task per node. I'm just going to do this one simulation on this one node. The amount of time that I'm requesting this compute node is going to be 1 hour, 0 minutes, and 0 seconds. I forget what the PTY is, but we'll put it in there. Bash I. The I might be for interactive. I'm not sure, but this is how we request it. I've done it before, and so I know this works. So if I hit that, okay. So now note that first it had my username at Spartan. Now it has my username at node 01. So right now I'm running on one of these compute nodes. This is good. It worked. It let me grab one of these nodes. One was available right away, so it just gave it to me. So that's great. If people were using them all at the time, then there might have been a wait involved. But in this case, it worked out. Okay. So now I'm on this compute node. So now I can run a simulation, right? And I won't be bogging down the head node and messing things up for everyone else. So I've claimed this compute node, and we're going to work on it. Okay. So now back to the tutorial. The tutorial says that this is the shell command to run. So we have NAMD2. So that's the executable. Basically, so remember when we open things using VMD, we type VMD and then the file we wanted or whatever? It's the same idea here, or we did that with gedit as well. So if I type NAMD2 and then this file, that says use this program NAMD2, which I've already installed, and run this file and take the outputs from this, and send it. This tells me to send the output into a file we're going to call ubq wseq.log. And we have an ampersand at the end because that says that when I run this, I want it to run in the background. And what that means is if I have a terminal going and I run a program and then the terminal's just kind of showing me whatever that program's doing, then that's not running it in the background. But if I put the ampersand there, that says, like, go ahead and run this, but then I still want to be able to use my terminal to do other stuff. So that's why I have the ampersand there. And by the way, when you install NAMD, you have to make sure that NAMD knows how, or that you have to make sure that your profile in the sign-in, or sorry, that your bash profile knows how to find this executable. Let me show you that real quick. So let's see here. So I'll use the VI editor to show it to you. Let's see if I can remember what it is. There, I think it's, yeah. So I'm using VI, forget what this thing is called, tilde /.bashrc. So what this file is, let's look at it real quick here. So note that this is my profile that basically, like, when I log in, this makes sure that my terminal can find things. So because I have this line right here, I added this myself, this export path equals $path, all this. Basically, this is the path where the NAMD program lives. So it's NAMD no CUDA. Like, CUDA is basically that's a way of speeding up molecular. Well, it's a way of using GPUs, right? Graphical processing units. It's a way of using GPUs to speed up various programs. So CUDA is the language for doing that. And there's a version of NAMD that uses that, and there's a version that does not. And so I happen to enable this one because I'm not using that at the time. So anyway, this is the pathway so that, because if I don't have this, if I just say NAMD2 and run this stuff, the terminal is going to tell me I don't know what NAMD2 is. But because I have this included in this profile, I'm going to quit. Right? Remember, if I want to quit here, :Q exclamation point means quit and don't save any changes I made. It's a good habit. Like, if you just want to look at a file, even if you don't think you changed anything, like, just do that, because then if you change something and didn't realize it, then it won't change it. So I'm just in the habit of quit exclamation point when I want to quit, and I know I didn't write anything. Okay, so yeah, I thought I should mention that, so you're going to have to edit this file so that your system knows what NAMD2 is. But so I've already done this. There is the command that I need to run here. So I'm going to run that. So let's see here. So if I type NAMD and then hit tab, see, it finished it for me. And that's one way that you can confirm that your terminal does know what NAMD is, right? So if, okay, so there's that, UBQ, WS, EQ, conf. And I'm going to send this data to UBQ, WS, EQ.log. And this file doesn't exist yet, but I want it to create that, right? So if you notice when I listed the files there, this log file isn't there. So I'm creating this log file because basically as a NAMD simulation runs, it generates all kinds of output that it can send to the screen. So if I didn't send that anywhere, it would just send it to the terminal. It would just tell me whatever it's doing at the moment, and we'll take a look at that so you can see it. But it's much smarter to send it to a log file so that I can look at it later. Because if it just sends it to the terminal, if it just prints to terminal, once I close this terminal, that's gone forever, and I can't look at it. So if something went wrong with my simulation and maybe I logged off and let it run and came back, odds are I'm not going to be able to see what went wrong. So sending your stuff to a log file is a very good habit. Okay, and as I said, we add the ampersand at the end because I want this thing to run in the background. So if I run that, okay, we have that little number there. That means something's running. So now let me try something. So if I go ls-trl, so list it and put things in order with more data. If I do that, look at the very bottom. I have a log file now. This UBQ WSEQ log file says 10:49. That's what time it is right now, 10:49. So yeah, so it's creating this log file. It seems to be running. But what if I want to check on what's going on in the log file? Well, I could open it up with an editor, but the better way to sort of check what's going on is there's a Linux command called tail. And what tail will do, so I'll do tail, and I'm going to say -f. And basically what that does is it's going to keep running this. I can't remember what F stands for, but I know what it does, basically. So if you go tail-f and ubq ws eq.log. So what I'm going to do is, so actually let me run it without the F first. So if I run just the tail function, see how it spit out these numbers? These numbers are inside that log file. That's where they came from. So that's what tail does, is it shows you the last, I forget the number, like the last 10 lines of a file or something like that. So that's what tail does. And you can change the number of lines it shows you too. You can put another flag for that if you wanted, but I never need to. Not typically. So let's see. Okay, so what if I want to just kind of follow this thing as it runs? Another thing I can do now is I can go tail -f and then ubq ws eq.log. So if I want to just kind of watch this as it goes, so I'm watching this thing. So NAMD is telling me what it's doing while it's doing it. So the simulation's running. So this is good. Let's see. It just it just wrote a restart file at 10,000 steps. So remember these restart files. We save that. Okay, calculated some energies. It's saving the restart files. So in case this thing crashes, I don't have to start from the very beginning again. It's writing coordinates to the DCD file. So remember, these are the files that store the trajectories. Let's see, it's telling me how much memory it's using. That's cool. So when the folks who created NAMD created the program, like they did all of this. When they wrote this, like they decided what information would probably be helpful to know as this thing is running, and they wrote it so that it did this. So this is really cool. Let's see here. It's writing the velocities. Let's see here. Yep, writing restart velocities. Okay, storing the velocities is really important if this thing crashes. Just having the positions isn't enough, right? Let's see here. Okay, so this thing is running. What step are we at here? We're at step 1750. All right, so let's see. This thing goes to, I think it goes to 2,500 steps. So it's getting there. It's at 1750. So let's say, all right, I'm watching this thing and I've seen enough. I want to go do other things. Well, the way to stop this tail function from dumping what's in that file to the terminal is I hit Control C. So that's cancel. Control C, and that cancels it. So now I'm back in the terminal and I can list things. Let me list TRL. Oh, by the way, another terminal trick is if you hit the up arrow key, it goes through all the commands that you've run recently. So if you know you just ran a command recently that you need again, use the arrow keys up and down, and that'll go to commands that you've recently run. So this will also save you a lot of typing. Cool. So that is pretty much what I wanted to show you, is just how to get a simulation started and running. Let's see. Let's wait till it finishes though. Let's get that tail again. See where we are now. So again, I just ran that tail-f and then the log file. Oh, I think it just finished. We just caught the end. How about that? Good timing. Yeah, writing velocities output file at step 2600. So yeah, I think this is done. Oh, look, it tells us how much wall clock time it took and CPU time. So 261, that's in seconds. So it took roughly 262 seconds for this thing to run. And it tells us how much CPU time it took as well. So yeah, all valuable information. Here, let me hit Control C again, because this is the tail-f function. It's going to keep dumping this to the screen. Even though nothing's changing in the file, it's still putting this out to the screen. So I still have to say Control C to cancel that. Oh look, and then we got this little message that this job that I ran is done. Well, let's look what's in this directory now. So now if I go list-trl, all the most recent stuff's at the bottom. Look at how many more files we have now. So it used to be that this was the most recent thing in here, right? And now we've got restart files. So let's see, we've got we've got all kinds of restart files here. For the coordinates, the velocity, XSC, and we've got our DCD for our trajectory, coordinates, the velocity, and then our log file. So it created all these new files for us, and then if we wanted to see this thing moving, then we could load this into VMD and take a look at that. Okay, so now that this simulation is done, I no longer need this compute node, right? So I can just go back to the head node since I'm not going to be doing more calculations right now. So the way I do that is by simply typing exit and take a look here, right? It says node 1. I'm on node 1. If I type exit, now it says I'm back on Spartan 01. Spartan 01 is the head node. That's how I know what node I'm on. So now I'm on the head node. I'm still in the same place, right? And I can list my stuff. Where is it? The list. I'll just type it again. List TRL. There it is. Yeah, I'm still in the same place, but now I'm in the same place using a different compute node. Now I'm on the head node again, or one of the head nodes. There's Spartan 1 and Spartan 2. These are both head nodes on the Spartan HPC. Okay, so now that we've run a simulation, let's take a look at the results. So as I said, this is a molecular dynamics simulation. This is dynamics. We want to see things moving. So let's just take a quick peek at what our simulation produced. So right now I am still in the directory where I'm still in the directory where the simulation was run. So this is where the DCD files are, right? So if I list DCD, okay, only one DCD file was produced. There it is. That's the thing that's going to store the trajectory data, i.e., where all the atoms are at each time, right? So the positions of the atoms as a function of time. So that's where this information is. So let's just take this entire directory and make a tarball out of it. So I'm going to go up a level, and everything I need is in the 1.1 build. So I'm just going to make a tarball of that. I'm going to call it, let's go tar-c for create, C, VF, V for verbose. And then I'm going to say 1.1 build. I'm going to call this thing 1.1 build post sim, because I did the sim, .tar, because it's a tar file. And then we want to tar everything that's in the 1.1 build directory. So now I execute that. List, there's my new file. So now I have this file 1.1 build. So now what I'm going to do is I'm going to want to move this back to my local computer, right? Because I want to open this up locally. I don't want to work on the cluster anymore because I can't do the graphical stuff there. So I need to move this data back to my computer so I can actually look at it. So the way we're going to do this is, again, we're going to use SCP. And let's see. So I have to figure out where this is. So it's in this directory path right here. And so I'm going to have to SCP that to my local computer. So what I'm going to do with that, remember this terminal, this is on my local computer right here. So I'm going to make this a little bit bigger. Easier, it's too big. There we go. So I'm going to make this shell a bit bigger. And again, that's just a control plus or control minus makes your terminal bigger or smaller. So I have to navigate to where I want to put this thing. So I'm just going to go to the desktop just to make life simple. So CD to get to the desktop. I'm in the desktop, whatever. All right, and now let's SCP this thing here. So the way we do it is on the machine where I want it to go, i.e. my local machine right here. This terminal is on the local machine. I go SCP for secure copy, and then I have to put my username at one of the head nodes, spartan1.sjsu.edu, and then a colon, and then I have to put where this file is. So we have the colon, and then I hit the tilde, and then /, and then let me see where this thing is. So this is on. So the tilde means go home. So when I'm on the cluster, then home is this my username here. So if I just copy this part, that's where this thing lives. So I'll copy that, put that here. Actually, I don't think I need this slash because this is going to include a slash, I believe. Yes. So that's where it is. And now I need the file name. So the file name is this tar file that I just made. If I copy that, I'm going to want to put this here. I pasted that. And now you have to tell it where you want it to be. And if basically in the terminal for like here is just dot or dot slash. If I do, actually I just do the dot. So if I go dot, that means put it in the directory where I am. I'm on the desktop. I'm going to put this thing on the desktop. So I'm going to run this thing. I'm going to move this over. So hopefully we can see this thing appear on the left. If I did everything right, we'll find out. So I hit enter. It asks for a password. That's a good sign that things are going the right way. Entered my password. Okay, do you see? Is something coming here? Yeah, you see this 1.1 build post sim? That was not on my desktop before, right? It just moved there. So yeah, we see 100%, it made it. So I just transferred that. So I transferred this file that is, you know, this is on campus somewhere. This file is on campus, and now it is on my desktop sitting on my table right now. So now it's here. So now we can look at this thing. So let's take a look at it. So where is it? 1.1 build. So this is the tar file. Let's see. I'm going to untar it using the terminal. Actually, I don't have to, but I might as well because we should get in the habit of doing this. So on the desktop, if I list everything, list-trl, ls-trl, we see 1.1 build postsim.tar. That's the most recent thing. Good, it's there. So I go tar-xvf. Whoops, 1.1 build. There it is. So if I do that, there it is. Now I have a new file, a new folder here, or directory is really what we call these things, right? So if I click on that, now we've got all these files. Okay, cool. So now for VMD, I'm gonna go into that. So if I go cd change directory, 1.1 build, now I'm here. There's all my files. Okay, I'm gonna open up VMD while I'm in here now. So VMD. Now this terminal is running VMD. And now let's load the molecule. New molecule. Let's see, it's already in the right directory because I moved there first. And let's see, the PDB that we created for this thing, it was like, the original one is 1 UBQ, but that's not the one we want to use, right? That was just the raw PDB. It didn't have any hydrogens on it. We want the cleaned up one. Let's see, yeah, let's do UBQ. .wspdb. Let's load that one because this is the one that has the water sphere. So if I load that, or double click that, and I hit load, cool, there it is. It's in here. But as I promised you, this thing was going to move now, right? So we need to load some data for this thing. So notice how over here it says load files for, and yeah, this molecule, we're going to load files for that molecule. So let's find that DCD file. There it is. That's the DCV file. Double click that. And now I'm going to say, let me load. I'm just going to click the load button. Okay, did you notice how it moved a little bit? So this is not a long trajectory, right? This is a short trajectory because we were just running a quick simulation. Well, let's see. Yeah, this thing's moving now. All right, so basically, you know, it doesn't look like much because it's you know, we only have 10 steps in our simulation here, right? And that's because of the output frequency, right? If I wanted to see a little bit more detail in the amount of simulation that ran, I could have put more there. But basically, this thing loaded, and now we can watch it. And you know, let's review going back to representations. So let's see. Let's make our let's leave the water as it is. Actually, let's create a rep. So we have this thing. Let's create a rep. Go back to this one. Let's say this one's just water. So now that one's only water. If I turn this one off, see how that's that now. And this one's all, but let's make this thing not water so that it's only the protein. And now let's make this drawing method. Let's do, where's cartoon? New cartoon. I like new cartoon. That's cool. All right, let's watch this thing go now. Maybe this will be cool. Yeah, so there's not a lot of data here. Let's slow it down a little bit to make it a little more. There we go. So there's something. So this thing's moving now. This thing looks like it wants to extend a little bit. But okay, so basically I just wanted to show you a little bit of how to take data from a simulation you ran and then watch it move in a simulation, and watch it move using VMD. So we moved the files to the local back to the local computer using the secure copy SCP, and then once they were back, we're able to open them up with VMD and take a look at what this thing's doing. So, all right, I hope this was also helpful, and good luck.